Best teaching assistant ever was a comment that I got from one of my physics students. And that's what I can be for you today on High Peak Education. Okay, so here we go. It says a baseball is thrown from the roof of a 22.0 meter tall building with an initial velocity of magnitude 12.0 meters per second, directed at an angle of 53.1 degrees above the horizontal. What is the speed of the ball just before it strikes the ground? Use energy methods and ignore air resistance. B, what is the answer for part A if the initial velocity is at an angle of 53.1 degrees below the horizontal? If the effects of air resistance are included, will part A or B give a higher speed? So first of all, we're asked to use energy methods and ignore air resistance, especially in part A. So it turns out that if you use kinematics and two-dimensional motion, you could figure out the speed of the ball just before it strikes the ground. But I'm going to suggest that the energy method should be just as straightforward. Let's talk about this. We have a building, and then here's our person standing here. We're going to throw the ball off this building. We're going to throw it at this angle, and it's going to have a projectile like this, right? And we're interested in what the speed of the ball is just before it strikes the ground. So let's call this position 1, and let's call this position 2. That is the start and the end. With all that said, we now have established that if we're using energy methods, do the vector directions and all that really matter? No, because energy is a scalar, right? So we're just going to use conservation of energy. And in fact, what kind of energy specifically, since we're ignoring air resistance? It's the conservation of mechanical energy, because mechanical energy is kinetic energy plus potential energy. So remember, linear momentum is not conserved in this case because there's a net external force from gravity acceleration. And conservation of mechanical energy. Now the conservation of mechanical energy says that the kinetic energy at point 1 plus the potential energy at point 1, what does that equal to? Conservation of mechanical energy. Remember, mechanical energy is just the sum of Ke plus Pe. The sum of kinetic energy plus potential energy. If that's conserved, then whatever it was at position 1 should equal at position 2. Does that make sense? The initial height is known. I labeled that as h1. Also, do we know the initial velocity of the ball? Yeah, 12.0 meters per second. So the initial velocity is this vector that it's taking off with from here, right? So we are interested in the final velocity of the ball when it's just about to strike the ground. So let's put that as v2 equals question mark. Now let me ask you this. Just before the ball strikes the ground, what are we going to assume that the final height is equal to? h2 is equal to 0. Now here's a question. Does the angle matter? It turns out the angle does not matter in terms of its speed that it hits the ground. What's the other thing that matters? The initial speed. So given that's the case, we'll say, fine, what's the expressions that we can write down for KE1, PE1, KE2, and PE2? So 1/2 mass velocity squared. What's the expression for the initial potential energy? Remember, it's mgh, but let's do h1 specifically. We're assigning the subscript of 1 to make sure we distinguish start position initial 1 versus end final position 2. Would the expressions look very similar for final kinetic energy and final potential energy? Yeah, it's going to be very similar. It's the exact same equations, except we're not going to use subscript 1. Let's talk about how we're going to simplify this. So what is the first simplification you could think of that we can make this calculation easier? Again, without plugging any of the numbers in, except if a number causes something to go away. So one of the simplifications is let the final potential energy term be 0 because the height is at ground level, which usually we assign ground level to just be 0. So we're just not even going to include it in just a moment. Let's do another simplification. Since mass is in all of the terms, can we divide the whole equation by mass? Yes, and check this out. They all cancel. As in many conservation of energy problems, the final result is independent of mass. you can divide the equation through by m to simplify. Now, the last simplification I kind of feel like is not as obvious. How do I get rid of these 1/2? I just need to multiply the equation by 2. So the last simplification is multiply the equation through by 2 to remove the 1/2 fractions. So with all those simplifications, this equation is going to be pretty straightforward. We say this term is 0, these masses all knock out, and then you can multiply everything by 2. The 1/2 goes away, so you're just going to get v1 squared plus 2gh1 is equal to v2 squared. Now, I don't know what you think, but that's quite a bit easier. One of the terms is gone, just 0. No fractions left because multiplied by 2, and we divided the masses out so you don't have to write m. Now, what's the very last step that we need to do to solve for v2? Yeah, take the square root of both sides. So what that means is we're going to have v2 is equal to the square root of the v1 squared plus 2gh1. And do we have all those quantities that we can put the numbers into the calculation? Because we have v1, we have h1, and we always have g. So let's actually get this going. The v1 was 12 meters per second. That was shown on the previous slide here. Do we always know the value of g? It's the gravity acceleration, which is meters per second squared. And then h1, that was the height of the building given, 22.0 meters. And go ahead and give that a shot on your calculator. Hopefully you get the same thing that I do. So v2, yeah, meters per second. That was the answer to part A. Let's move on to part B. It says, what is the answer for part A if the initial velocity is at an angle of 53.1 degrees below the horizontal? Well, once again, we already kind of talked about this. Does the angle matter? If it's positive 53.1 degrees or negative 53.1 degrees? Well, in part A, it's positive 53.1 degrees. But if we throw the ball this way, downward, does it really matter? No, it doesn't. It will hit the ground at a different angle, but it will hit with the same speed. We determined that the angle was not involved in the earlier calculation of part A. So the speed of striking the ground will be the same, even if we throw the ball below the horizontal instead of above the horizontal. Will the details of the trajectory be different? In other words, will it be in the air a different amount of time, and will it hit the ground with a different final angle? Yeah, the details of the trajectory will be different, as it will be in the air less time when thrown below horizontal, and will strike the ground at a different final angle. But these do not affect the final speed through energy conservation. Let's see if we can come up with a physical reason why. Because if you throw it up and then it comes back down, will it be moving the same speed as if you just threw it downward? I'm actually going to say yes. Because if you throw it up, the gravity is going to slow it down in its y velocity, but then you're going to speed it up in its y velocity as if you just threw it below horizontal. So if you throw it up, it will end up having the same speed on the way down across from the building. So just like if you had thrown it downward. So this is why we get the same final answer. We don't need to repeat the calculation. Okay, now we're going to do part C. If the effects of air resistance are included, will part A or B give a higher speed? Now think about this. If they ever ask you to think about air resistance, which is closer to real life, they will only have you think about it conceptually, not actually do the calculation. Notice they're not asking you to do the calculation of what's the speed going to be. They just want you to think about what's the number and which one's higher. So let's first discuss air resistance. Do you expect air resistance to increase, decrease, or keep the speed of the ball the same when it hits the ground? But in reality, will air resistance slow things down? Let's say in reality, there is real air resistance in the world so that the speed of the ball striking the ground is less than that was calculated in parts A and B. So that's the first thing we want to establish. But then the other thing is this. They actually really want us to compare parts A and B. In other words, will part A and B still be the same number, or will it be different, part A and B, if air resistance is included? It is going to be different. Now, what's really different about trajectory of A compared to the trajectory of B? It has an angle below horizontal, whereas A's angle is above horizontal. But let me ask you this. If A's is above horizontal and B's is below horizontal, which ball spends more time in the air? So since A spends more time in the air, is there more air resistance? Yes, so it ends up going slower in the end. Okay, so this is the important thing. We expect with air resistance, the final speed of A to be smaller than what was calculated, but even smaller than part B. This is because part A goes up then down, meaning this is a longer trajectory with more time in the air. Ball A has more air resistance, so it slows down for longer, hitting the ground with a slower. So that's it for this problem.